El Niño is one of the largest climate oscillations of the Earth's system. Interactions between the ocean and the atmosphere in the tropical Pacific create this non-periodic 3 to 4 year phenomenon. El Niño has large effects on terrestrial and marine ecosystems, as well as the global economy. This animation uses satellite data, illustrations, and computer models to describe our current knowledge of El Niño. The animation consists of 4 sections. The first section introduces important oceanography terms necessary to describe El Niño. The second section shows how El Niño begins in the equatorial region of the Pacific. The third section describes what happens near the coast of Peru during El Niño, explaining why anchovy near the coast of Peru disappeared during an El Niño event. Finally, the fourth section describes how El Niño returns to normal conditions. We begin by introducing 3 important oceanographic processes that are integral to an El Niño event: upwelling, the thermocline, and East-West Asymmetry. Ocean currents are driven by the wind and steered by the Earth's rotational force, known as the Coriolis force. In the northern hemisphere, these currents circulate in a clockwise pattern, and in the southern hemisphere, these currents circulate in a counterclockwise pattern. Upwelling is a water movement driven by wind and rotation. Forces from the Earth's rotation combine with strong winds to move surface waters away from the coast and bring deeper water to the surface to replace water that has been moved offshore. Upwelling occurs primarily along coastal regions and near the equator. Off the coast of Peru, equatorward winds force the surface of the water northward, and the Coriolis force pushes coastal waters westward and slightly northward. As a result of the overall westward water motion, deeper water near the coast moves towards the surface. The movement of deeper water moving towards the surface is called coastal upwelling. This figure shows observed water movement in the upwelling region off the coast of Peru. The x-axis is the distance from the Peruvian coastline and the y-axis is depth. Arrows describe the movement of upwelled water. Water at approximately 60 meters depth moves to the coast. Then the water moves slowly to the surface and away from the coast. The horizontal speed of water is around 5 centimeters per second, and the vertical speed is around 1/100th of a centimeter per second. Upwelling brings rich nutrients towards the surface if the source water originates from nutrient-rich water. This nutrient-rich water at the surface creates an abundance of phytoplankton and small pelagic fish, such as anchovies. Due to upwelling, Peru is famous around the world for its anchovy fisheries. The California and Benguela currents are also famous for their biologically rich coastal upwelling. Near the equator, winds blow to the west and push water westward. The Coriolis force moves water to the right in the northern hemisphere, which is northward, and to the left in the southern hemisphere, which is southward. Therefore, the Coriolis force moves surface waters away from the equator. Cooler, subsurface water upwells to replace the water that flowed away from the equator. This movement is called equatorial upwelling. This map shows the result of an ocean computer model of sea surface temperature in the Pacific Ocean at the equator. Warm waters are shown in red and cold waters are shown in blue. Notice the colder water in the eastern Pacific. Here, we focus on water temperature in the equatorial region of the Pacific Ocean. In the second panel, the x-axis is longitude from 100 degrees east to 80 degrees west. This distance is more than 19,000 kilometers. The y-axis is depth from the sea surface to 200 meters. The average depth of the Pacific Ocean is around 4,200 meters. This figure only shows the top 5% of the ocean. The colder water, shown in blue, is shallower in the western Pacific than in the eastern Pacific. This is due to the westward wind at the equator pushing the warm surface water to the west. The 20 degrees Celsius isotherm, shown in the bold line in the second panel, depicts the thermocline. A thermocline is an area of rapid temperature change. In general, water below a thermocline is higher in nutrients than water above a thermocline. Scientists use the depth of the 20 degrees Celsius thermocline in the equatorial region of the Pacific Ocean to determine if an El Niño event is occurring. In normal years, the 20 degrees Celsius thermocline is deeper in the western boundary region and shallower in the eastern boundary region. But during El Niño, this thermocline becomes flattened. Upwelling in the eastern equatorial Pacific Ocean brings cool water towards the surface. In the western Pacific Ocean, little or no cool water is upwelled. Therefore, the eastern boundary region of the Pacific is normally colder than the western boundary region. This difference in surface temperature is referred to as the East-West Ocean temperature asymmetry. Warmer waters in the western Pacific region make the air temperature warmer and cause it to rise higher in the atmosphere. This air movement creates the Indonesian low pressure system, which brings intense rainfall to the western Pacific. On the other hand, in the eastern Pacific Ocean, the cooler upwelled water creates the high pressure system. This low and high pressure system in the equator region causes westward airflow near the surface of the ocean. The difference in air pressure near the ocean surface is referred to as the East-West Atmospheric Pressure Asymmetry. Wind created by the East-West Atmospheric Pressure Asymmetry reinforces the East-West Ocean Temperature Asymmetry. In this way, these two are interrelated and influence each other.